Okay, reminder that on Friday I'll be out of town, so our lecture that day will just be a recorded video on YouTube. I'll put the link on Blackboard, or you can just look at my channel on YouTube and find it there. The groundwater assignment that you have on your plates right now should be submitted to Blackboard before our exam on Monday. And so at 1 o'clock. And I'll give you the answer to that assignment. I'll email you the answers so that you know if you're on track, but I'm not going to email you the full solution because I want you to do the calculations. Remember that we talked about the exam parameters in a previous class meeting, and there the instructions were that you should prepare an equation sheet that does not include any terminology definitions. It shouldn't include conceptual information, so it can have formulas and you can define terms in the formulas. So are there any questions related to the exam that we're going to have when we get together on Monday? So the coverage of the exam will be everything in the course up to and including the lecture video on Friday. Any questions at all? This is where we left off. We're talking about wells. A hole is dug in the ground and we want to get the water out because that's sometimes the best available water that we have access to. The quality of water underground is generally pretty good unless people have somehow spoiled it with chemicals, or if the water table is really close to the ground, sometimes they can say that the groundwater is under the influence of surface water. So for example, if you had an agricultural field, like cattle on a field, you wouldn't want to pump water that was 15 feet underground because most likely the water table that shallow wouldn't have yet had all of the pathogens decay and be removed. But if you have an agricultural field and you dig down 200 feet and you go through multiple layers of clay and rock, the water down there most likely is not under the influence of the water at the surface. Even if eventually the water from the surface gets down to that deep well, it's going to take long enough that all of the soil microorganisms are going to break down any pathogens. That there aren't suitable nutrients to sustain the cryptosporidium or E. coli that would make you sick from the cow waste by the time it gets months or years down through the soil layer and to that groundwater. So we pump water out because we want the water. And initially, before we turn the well on, the water table is flat. But when we turn on the pump and begin withdrawing the water, you take a liter of water out and water has to migrate towards the well casing to replace it. And so why does water migrate from over here sideways? Like if initially the water table is flat, what's the driving force that causes water to move towards the well? It's that when you withdraw water, you're going to be depressing the water depth a little bit inside of the casing. Like if initially the water level inside the casing was like a pool of water and you withdraw it, that's going to make the water level inside the casing a little bit lower. And then you take more water out and the water level's a little bit lower. And so eventually you're making it lower and lower and lower, and then the water that was to the side of the well casing is going to move in sideways because we have an area of low energy. And so water flows from high energy over here where the water depth elevation is high towards low energy. So here where we have drawdown, excuse me, drawdown is depression of the water level in the proximity of the well. Hydraulic conductivity we've talked about in several class meetings. It's a soil property that you can determine in the field or in the lab, and it measures the ability of fluid to move through a soil, and it has units of length per time. And so one common way that we'd see it would be centimeters per second, or it could be expressed in terms of meters per day. The thickness of the aquifer is the distance vertically from the bottom confining layer up to the water surface. And in some cases, it's a distance between two confining layers. If we have a confined aquifer, and we'll distinguish today between unconfined and confined aquifers because we have different equations that we use to relate flow rate and drawdowns in those two different types of aquifers. Transmissivity is a combined parameter where we're merging together the thickness of the aquifer and the hydraulic conductivity. Because if you have some soil that has a high hydraulic conductivity and you have a thick aquifer thickness, so a large B and a large K, then that would mean that you could get a lot of flow out of a well. And so this combined parameter is what we substitute into some equations rather than treating the hydraulic conductivity and the aquifer thickness separately. But it's not necessary that we combine it, but it's just a term of convenience. In an unconfined aquifer, it is the actual water surface that's being drawn down. If it's a confined aquifer, though, it's the pressure that is being drawn down. And it's not the water elevation, but it's the pressure. So I'll show you what that looks like in a diagram in a moment. But when we're measuring the reduction in pressure as water flows towards a well, then we'd be measuring its piezometric head. And so piezometric head is the sum of the pressure head and the elevation at any given location. Last time we discussed porosity and how that is a measurement of the non-solid space inside of a soil. And then the effective porosity is those combined or interconnected voids that can be used to transmit water. All right. Now, this is a confined aquifer, and look how this is different from the figure that I showed you a moment ago with drawdown. So here's the drawdown in an unconfined aquifer. And so this is the actual water surface that's going down. So on the bottom, we have clay or rock, something that doesn't transmit water at the bottom. So that's, this aquifer is up on top of that impermeable layer. And then the water surface is getting lower and lower as the water draws nearer to the well. This is unconfined. But a confined aquifer is one that has a lid on top of the aquifer. And so this cross-hatching here is representing the fact that we have a clay layer down beneath and then a layer of sandy or gravel or just permeable soil with thickness B. And then there is another confining layer above it. And so the confined layer thickness that we're interested in here is measured with this vertical parameter B. And we could do some measurements to find out what's the hydraulic conductivity of this layer and find the K value. And if we multiply, remember, K times B, then that is here in this formula transmissivity. But what's being drawn down isn't the water elevation, because even though the water's migrating sideways towards the well, the highest the water can go in here is the top of the confining, is the upper confining layer. So the water can't go above here unless we drill a hole through the confining layer. Like if we put in a monitoring well, this is a production well where the water is being withdrawn. But a monitoring well would be a hole that we dig down, and we're not going to take water out, but we're just going to measure how deep is it from the surface to where the water level would rise if we punctured the confined aquifer. So it's like this is a pressurized sponge. There's water flowing through this porous medium towards the well casings, and if we puncture that top layer, this top layer that is impermeable, then the water level would rise up out of there, but it would eventually, stop at a point. And that's what this curve is. The curve that here is being described as the piezometric surface. Some publications will refer to it as the phoratic surface. Those two names mean the same thing. It's the height that the water level would rise to if we put in a piezometer. Or it's just a representation of how pressurized this well is. How pressurized the aquifer is. So this formula allows us to to relate how far away we are from the production well. So R1 and R2 is the distance from the production well to some points that we're just measuring the top view distance from here to here. 1, by definition, is going to be the nearer of the two locations, and location 2 will always be the location that's further away. That's how we define 1 and 2. 1 is closer, 2 is further away. And so H is talking about how high the water surface would rise to at those points. And so it's not the actual physical height of the water, because if we're using the bottom of the aquifer as our elevation datum, the physical height of the water is only going to be as high as B. So what we're measuring with H is how high the water level would rise if we punctured it. Or in other words, it is the piezometric head. So it's the pressure head plus the elevation that H is measuring. And then Q sub W is going to be the flow rate out of the well. So let's think in terms of units. Is this dimensionally homogeneous, this equation? Dimensionally homogeneous means, do you have the same units on the right-hand side of the equation as you do on the left-hand side of the equation? Okay, so 2 and pi, we don't get any units there. What about transmissivity? What are going to be the units of transmissivity if that is K times B? So K would be length per time, so maybe it's meters per day. And then B is the height of the aquifer, the thickness of it, so that's units of meters. So with the transmissivity, we've got meters squared per day, and then we're going to multiply it by H. So head has units of meters, and so in the numerator, we've got the meters squared per day, and then we multiplied it by the H units of meters, so cubic meters per day. And that is what we'd expect for a volumetric flow rate to have. Now down here in the denominator, are we missing any units there? Not if it's the logarithm of a ratio. The ratio cancels out the units of meters and meters. And so down in the denominator, it's a unitless expression. So this is dimensionally homogeneous. It makes sense that we'd be able to predict the flow rate Q by combining these parameters together. Now this equation above it is the same formula. These are the same equation. It's just this top equation is saying, what if location 1 is the radius of the well? So R sub W is saying, instead of having location 1 being some distance away from the well, let's just substitute in the well radius there. And then H sub W is the height of the water inside of the well. So that would be H1. So R1 is the radius of the well. H1 is the depth of water in the well. This is just saying you could find the height of the phoretic surface at any radius away from the well using this equation. So it's just rearranging the equation below it to solve for H2 at some distance, R2. So any questions so far about a confined aquifer? This is what the FE reference manual looks like. So this is how our textbook presents it. This is how the FE reference manual presents it. Looks the same, except for they've defined the units in traditional terms. So it's described as the Thiem equation. Here we've got the same things that we've talked about before, an impermeable layer underneath, some aquifer thickness B. There's an aquitard through which the water cannot flow upward. And so we've got a pressurized permeable soil layer, and the water level would rise to some distance here. And so H1 and H2 are the heights of the piezometric surface. It's not the physical water surface that we're measuring. It's just the tracing of the pressure surface. So if we punctured that pressurized confined layer with a piezometer, it's how high the water level would rise to. to express the pressure distribution. Okay, let's practice. We have a confined aquifer that has a hydraulic conductivity of 20 meters per day. So K is 20 meters per day, and the aquifer thickness is 6.6 meters. So we can first of all calculate the transmissivity, because it is the 20 meters per day multiplied by the 6.6 thickness, and the transmissivity of this particular aquifer is 132 meters squared per day. Okay, and what we know is that the initial piezometric surface, it has an initial piezometric surface of 14.3 meters above the lower confining layer. So this is 6.6, and before pumping occurs, the water level is from the bottom up to the water surface, 14.53. So that's capital H. That's telling us capital H is 14.53 meters. All right, what flow rate will cause the piezometric surface to be at 13.85 meters at a radius of 40 and at 14.31 meters at a radius of 85 meters? Okay, so what we've been given in both of these locations is H. Sometimes in problems like this, they'll tell you the drawdown. And so if they were telling you the drawdown, then you'd have to determine H by this lowercase h, by subtracting the drawdown from capital H. But this is a simple one because they're giving you H2 and H1 directly. You don't have to do that conversion to drawdown. So what we have is R1 some value and R2 some value. Do you remember which is 1 and which is 2? 1 is the closer location. So the closer location is 40 meters. So R1 is 40 meters and R2 is 85 meters. And the height of the piezometric surface at the closer one is 13.85 meters, and then H2 is 14.31 meters. Now, does that make sense? Is that reasonable based on what we know the shape of the curve should be? The closer you get to the well, the height of the piezometric surface should be lower. So that is what we see. When we're 40 meters from the well, the water height, the height of the piezometric surface is 13.85, but then 85. Further away, the height of the piezometric surface is 14.31. Just as a side quest, let me ask you, what is the drawdown at 1? Drawdown at 1. Does anybody know how to calculate what's the drawdown at 1? Anyone willing to speculate? Brave soul. It's the initial height of 14.53 minus the current height. So the drawdown at 1 is 14.53 minus 13.85. So right now the water has been depressed compared to where it ordinarily is, the ordinary height of 14.53 meters. The pumping has drawn the water down 13.85, 0.68, 0.68 meters. That's the drawdown at 1. You don't need that for what we're going to be solving, but some of the problems I'll give you the drawdown rather than giving you H1. I would tell you what is S1. Drawdown S1. Okay, back to the main question though. How do we find out what is the flow rate that comes from this? Well, we know R1, we know R2, We know T, HT, H2, and H1. Let me pause and let you put that into your calculator. Find out what is the cubic meters per day that we're getting from this well. For the conditions that are described, what kind of capacity is this well able to generate? So just to summarize, we interpreted from the given details that the closer location was location 1, where we're 40 meters from the well. The height of the piezometric surface from the bottom was 13.85. Then at 85, it was 14.31. So substitute all of that in. We should get 506 cubic meters per day. I've written a lot of questions like this for the FE exam, and you actually have to be careful because you can write questions that are like numerically impossible pretty easily. Like you could sometimes ask people to solve for the height given a flow rate, or solve for the drawdown given a flow rate, and I always have to be really careful when I write questions like this because that logarithm function, it being a ratio of radiuses, it's just tricky writing them. So anyways, I have a second part of this problem. I'm going to give you a handout so that you can maybe, you're not going to have to turn this in. This is just for you. But so that you've got a good look at what the well looks like. Let's do the second part of this. What's the water depth of the well if the diameter of the well is half a meter? So if the water depth what is the water depth of the well if the diameter of the well is 0.5? So this formula, you use R as one of the distances. So think about how can you use this equation to find out how deep the water is at the well. I'll give you a clue in a minute, but I want you to think about it for a bit. What's the relationship between diameter and radius? If we've got a, let me just do a top view here. We've got a well that the diameter is 0.5 meters. Is that what it says? Yeah, 0.5 meters. So that is this distance here, the diameter. And what's the radius? 0.25, just half that, right. So R equals 0.25. So in this equation, what are you going to use as the 0.25? That, you set that equal to R1. So we're just saying, let's have the closer location be the edge of the well. And so H1 will be the water depth. R1 will be the radius of the well. And then the 2, location 2, can be either of the other spots that we know stuff. It can either be the location that's 40 meters away and a height of 13.85, or it could be the location 85 meters away where the water height is 14.31. It can be either one, and we're going to get the same answer regardless. Through on your calculations. Hopefully some people will do this first location, some will do the other, and we'll just verify that it doesn't matter either way. All right, so let R1 be 0.25, let H1 be unknown. We know the Q, we know H2 and R2 depending on which one we pick. So first things first, I guess, rearranging the equation to solve for H1, the height of the water at the well. So H1 will be H2 minus flow rate through the well, the logarithm of the radius ratio, and then in the denominator 2 times the transmissivity. So I used the 40 meter distance. Did anybody use the 85 meter distance? Okay. Did you end up with the same 10.75 meters? All right. So there's a curve. The water surface is a curve. And so far between these two examples, we identified 3 different points along that curve. We identified the location right at the well itself, where the water height was 10.75. And then 40 meters away, the water height was 13.85. 85 meters away, the water height was 14.31. And if we keep going further and further, eventually the water is going to get up to 14.53 meters. You don't have to go infinity meters away. There is some definitive range where we could say, well, it's within maybe a millimeter height, and you'd be able to calculate the distance to where it's back to its equilibrium height. Like that's the zone of influence for drawdown. But in any case, this is, remember, is a confined aquifer. So this surface is only the actual water elevation if we puncture the confined aquifer with a piezometer, and the water level would rise inside that piezometer tube to reflect the amount of pressure inside of that confined aquifer. Remember, what causes a confined aquifer to be pressurized? It's typically when we have some topography with like a hillside that's getting recharged, and then a confining layer that starts off as vertically oriented and then becomes horizontally oriented. And so the perched recharge in one location causes pressurization in the confined layer. So any questions about the example where we've just used the Thiem equation to find out the both the flow rate that we could generate and then also how deep the water would be in the well? Any questions at all? Yeah.
How would it be different if you just gave the drawdown? Like, how would you word it?
Ah, good. Yeah. So how would that question look like? Let me just show you. Let me give you a quiz question real quick, like a hypothetical. Thickness will cause the drawdown at a radius to be 0.5 meters and a drawdown of 0.15 meters at 85 meters. So that's an example of what it would look like if I specified the problem in terms of drawdown instead of water height. So like the number one popular mistake, like the most popular mistake when I give a question like this is that people would put the drawdowns as H. And drawdown isn't H. Drawdown is this distance right here. So drawdown is from the height that the water normally goes to where the surface is. This is the drawdown. The formula doesn't want that little amount. The formula wants this big amount. So if you're given the drawdown, you'd need to calculate the H's based on this initial height that would be given. So H is defined, the overall H, given the drawdown. So it's just one additional step to find the H's. Great question. Are there any others? Okay. Well, now let's talk about unconfined aquifers. The situation is just a little more complicated if we have an unconfined aquifer. What we were looking at before, the confined aquifer is distinguished by having both a lower confining layer and an upper confining layer, and then the permeable layer that we're interested in is between them. Here we only have the lower confining layer. So there's the water perched on top of this clay or rock layer, and then just soil beneath it. And so this curve is the actual physical water surface. It's not the phreatic surface. It's not some imaginary line that's describing the pressure distribution inside of the aquifer. This is the actual water surface. So if you look at the formula, it looks pretty similar, but instead of transmissivity times some expression of the heights, it's only the hydraulic conductivity. And then now, instead of just the difference in the heights, it's the difference in the heights squared. So it's because it looks pretty similar, it's easy to forget that there's different equations for a confined aquifer versus an unconfined aquifer. But you have to pay special attention to that because the unconfined aquifer equation is slightly different. This is what it looks like in the FE reference manual, Dupuit's formula. So the only difference here is that they are defining the units in terms of traditional. So they're saying cubic feet per second, the hydraulic conductivity, what if it was expressed in feet per second? But we wouldn't be thrown off by that. All right, this example I think is on the back side of the paper that I've just given you. Were there any extras, by the way? Okay, so a well is pumping 0.4 cubic meters per second, so we're given the Q, an unconfined aquifer, so we use Dupuit's formula. Saturated thickness is 24 meters, so that is H. The thickness of the aquifer that would have water in it prior to drawdown. And now, the drawdown 50 meters is 1 meter, and the drawdown 100 meters from the well is 0.5 meters. Okay, so this is an example where I'm giving you the drawdown rather than the water height at those locations. So you're just going to need to do the subtraction to find out, from the initial saturated thickness, what will be the water elevation with the drawdowns that are described. So the first thing I'd like you to do is determine what's the hydraulic conductivity. So if you look at Dupuit's formula, the only unknown is K, because we know the flow rate, we know the H's, we know the radiuses. K is the only unknown. So first solve for the hydraulic conductivity, and then find out at a radius 5 meters from the well, what's the drawdown there. And I've got drawdown in bold because when you solve for R1, you're gonna when you use 5 meters as R1, you'll be able to solve for H1, but that's not the drawdown. That's the height of the water at that location. So it's going to be one final additional step to take the H1 that you solve for and get the drawdown from it, because I want to know the difference between the initial saturated thickness and the height of the water after pumping occurs. All right. So let me pause. Feel free to interact with each other, discuss, check answers, and all of that. And I've got the solution if you want to check it as you go along. All right. So I've sketched up on the whiteboard how we can find H1 and H2 from the drawdowns that are defined. So if the drawdown at location 1 is 1 meter, then the saturated thickness minus the drawdown gives us the height of the water at location 1. So 23 meters at location 1, 23.5 meters at location 2. Then we do the algebra, isolate K instead of flow rate, Q. So rearranging that formula to solve for the K and then substitute in everything we know. I've got all my units written there. Do some intermediate steps. 3.8 times 10 to the minus third meters per second. Okay, so that's the hydraulic conductivity. Now that we have the hydraulic conductivity, we can determine the drawdown 5 meters from the well. So if we're talking about a distance 5 meters away, that's going to be the new R1. And we can use either of the other two locations as R2. Looks like I used the further one. So we're trying to find out, first of all, what's H1 at this new location. And then once we have the H1, we'll find the drawdown. So substituting it into the formula for H1. So this is me algebraically rearranging the formula to solve for H1 and getting successively sloppier, unfortunately. 21.26 meters will be the height of the water at that location. So then the drawdown is the saturated thickness of 24 minus the height. So we have 2.74 meters of drawdown at a distance of 5 meters from the well. All right, it's 1:50. We're out of time for today. Remember that on Friday we won't have a meeting together in class. It'll be a recorded video. And then on Monday of next week, we're having a celebration of learning on Monday. Isn't that what Dr. Michelson calls them? Celebration of learning.